Lesson 5.2 is going to teach us how to solve systems of equations when we're using substitution. It's another method. You've already seen graphing, and graphing gives us a really great visual of our solution and really gets us to understand what the meaning of our solution is. We know it's the intersection of the two graphs for the equations in the system. But graphing has some, pretty substantial limitations, and a lot of times we don't have the tools to get a very, very precise graph, or even if we do, our answer may not be a whole number that lands really nicely on a graph where we can see it. If it's a decimal or a fraction, it becomes almost a guessing estimation game. So we have a few other tactics or strategies under our belt, and today we're going to talk about the second one, which is substitution. And substitution is going to be much more algebraic. It's going to let us use the algebra that we've been learning, moving terms, solving equations to get to the same solutions as we did with the graphing. So let's go ahead and get started. Let's first define this. So the substitution method, write that down, is used to eliminate one of the variables by replacement when we're solving a system. We'll say a system of equations here, be specific. So essentially, we already know that the predicament where we're solving an equation with more than one variable is that there's not a unique answer. And we're looking to see what is a unique answer if we have more than one equation, essentially. And the main idea here is to use substitution by solving for one of the equations for one of the unknown variables, and then sort of plugging that into the other. And so you have a nice description here and a nice step-by-step, but I'm just going to jump right into the examples because I think that's how we really get to understanding what's going on here. So when we were graphing, we really wanted both of our equations to be solved for y, ideally, almost like number 4 over here, because then we can use slope and intercept to graph. That's actually not a requirement in substitution. So in substitution, we want one of the equations to be solved for just one of the variables, and it doesn't matter which one, okay? So I only need one of the equations to have one variable isolated, and it could be x or y. I'm not going to be using slope or y-intercept or any of the standard or point slope. I'm not using any of that because I'm not graphing. So as long as one of my variables is completely by itself, I am ready to use substitution. So let's take a look at number 1. This first one is in standard form, which is fine. That's okay. When I notice down here, I have this bottom equation already is solved for y. Okay, so what's special is not the y necessarily, but just that this variable is by itself. And then this is what I'm going to do, guys. Basically, we're going to insert one equation into the other. So this is a pretty powerful statement. Let's talk about equations for just a moment. We want to remember that an equation means that these two quantities are equal. They're exactly the same. Therefore, they're interchangeable. So this bottom equation is telling me that y is exactly the same thing as 5 plus x. Okay? They're equal to each other. They are the exact same quantity. And what that's going to allow me to do is it's going to allow me to take that expression and substitute it or insert it anywhere I see a y. And I'm allowed to do that because this bottom equation is telling me that I can do that. It's telling me that they're exactly the same. So we're going to plug that in, kind of like sometimes we're like, oh, solve this for x equals 3, so we plug in a 3. We've done that before when we were solving functions and that sort of thing. Well, that's really what we're doing, except we are plugging in not just a number, but we're plugging in an expression. If y is equal to 5 plus x, then in this top equation, anywhere I see a y value, I can insert or substitute in or plug in that 5 plus x, right? So that's what we're going to do. We're going to, if this is already by itself and we're ready to rock and roll here, we're going to rewrite the other equation, right, the one that's not solved, and I'm going to copy it exactly the way it was. I don't want to change this equation. I want to definitely preserve what it valued, what it equals. So I've got 2x plus a 2. And the only change I'm going to make is that instead of saying 2y, instead of writing a y in that spot, I'm going to insert that 5 plus x in there. or substitute or plug it in, however you want to think of it. And then everything else stays the same, equals -10. Okay, so I've taken that top equation and I've rewritten it. Okay, 2x plus 2, and then instead of y, it's going to be 2 times this. I get to replace or substitute that in there. Everything else stayed the same. It's the same equation. And again, I've done this. I haven't done anything illegal here, mathematically speaking, because these are equal to each other. They're the same. But here's the advantage to what we just did. We now wrote an equation or a version of this that doesn't have 2 different variables. It has all just x's. And that means we can simplify and solve this. It actually becomes review. Simplify, we'll distribute, combine like terms, and then just solve for x, and we'll have our first value here. So it becomes just like solving equations like we did in Unit 1. So I've got 2x plus 2 times this quantity. This is another reason I wanted y'all to get used to plugging in parentheses. If I'm doing 2 times all of this, you want to make sure you distribute. And so when we do that, we've got 2x plus, now we have a 10 here. 2 times 5 is 10. Plus 2 times x is 2x. So we distribute, that gets rid of the parentheses. And then we do have a couple of like terms here. I want you to be able to look at this and recognize you've got a couple of 2x's on the same side that we can combine. So if I have 2x plus another 2x, I really have 4x's here with our 10. See, this is all review now. We're just simplifying, and now that it's fully simplified, we can start to solve. So now that this is simplified, we start doing those opposite or inverse operations. Get rid of the 10 by subtracting it on both sides. That leaves me with 4x equals a -20, since those are both negative, and then divide both sides by 4. And it turns out that x has to be -5. Now remember, be very careful with this. Everything we've done there, once we substituted that in, it became a complete review problem, right? But don't forget that our final answer is an ordered pair. And so we need not just the x coordinate, but also the y coordinate. So don't forget to go back in and find the y. But now that we know x, and since it's a solution in both of these, you should be able to plug that x value you just found into either one of these to find the other coordinate. And I think the bottom one is easier, although you could most definitely plug it into either one. I'm going to take that bottom one since it's already solved for y, which is what I want to find next. I'm going to say y is equal to 5 plus my x value, which I just found out was a -5. And then I just solved this for y. So 5 plus a -5 is just 0. And that must be the corresponding y coordinate here. And that now is my solution. So don't forget to find both the x and the y. Sometimes we get here and that feels so satisfying and like, final that we found x and we can move on. But don't forget, you got to go back and find y as well and give the ordered pair. And if we were to have graphed, if we had solved this top one for y and plugged it in the calculator or solved it by graphing by hand, this would have been where these two equations intersect. That is the solution to our system. We just found it using a different method. Okay, let's try another one. Let's try number 2. So on number 2, again, my number 1 goal is solve the equation for one of the variables if it isn't already. Sometimes it is. So that's the first thing I want to check for. This top one, again, looks like it's in standard form, but nothing is isolated. Not as far as variables anyway. But down here, hopefully you catch this, that x is by itself. So that's great news for us. It's totally fine that's an x as long as x is by itself. And I know x is equal to this. Then I can take that and insert it anywhere I see an x. So that's going to be my strategy here. Okay, I'm going to write this top equation up here again. So it's 2x. Oh, nope, sorry. See already. Not 2x. I'm going to plug that in. Let's just cross that out. So it's 2 parentheses, and instead of x, I'm going to insert what x is equal to. So I know that x is the same as 2y minus 1. That's what I'm going to throw right in there. Everything else I'm going to copy is exactly as it was in the original. So it's still 2 times this quantity minus y equals 3. The only thing I did was take that x out and throw that in there instead because they're equal. I'm allowed to do that. And then we'll distribute. Guys, it's unit 1 now. Once you do this, the rest is just, careful simplifying and solving which at this point we should be able to do hopefully like in our sleep practically. So negative 4y is our first product there. Then 2 times negative 1 is negative 2. We still have that negative y, don't forget, and the 3, and then you do have a couple of like terms here. So this is a negative 4 and a negative 1. When we combine that, we're going to get negative 5y's. And then minus 2 equals 3. After simplifying comes the solving. So let's start to isolate our variable. We'll move the 2 out of the way. That gives me 5 here, and then we'll divide both sides. Turns out that the y coordinate for this problem is negative 1. So this time we found the y first, and that is okay. So y is going to be our y coordinate, and then we'll use that to find x. Now we have this. We do one more substitution, plugging it back in. And again, you could do either one, but I do think that this one's a little easier since it's already solved. It's already organized the way we want. So I'm going to take this guy right here, x equals negative 2 times y, but now I know y is negative 1 minus 1. And then, so I'm just putting a negative 1 in there and solving. So that's a positive 2 minus 1, which is just 1. So apparently my x coordinate is positive 1. That's the full solution right there. I have to solve for both. And there it is. Try number 3 and see how that one goes, and then you can check your answer. Okay, so check your answer. You should get 1/2 and 1/2. This one was a little kind of cool because that bottom one, they're essentially both isolated. So you could either, since x is equal to y, it doesn't really matter which one you pick. You could put a y in here and solve it like I did, or you could put an x over here and solve it that way. Either way, you should get 1/2 for the first one, and then of course, since they're equal, once you know the first answer, the other one is exactly the same. So you should get 1/2, 1/2. All right, so we'll try one more really quickly. What I want to do is show you what happens if maybe one is not already isolated. So what I want to do is number 6 here as an example, because sometimes this is going to happen. In number 6, you notice both of these are in standard form. So neither of these are quite ready for us to jump right into substitution. We're going to need to reorganize one of these so that it lends itself to substituting. None of these variables are isolated, and that's a problem if we're trying to use this method. So I can pick any of these, okay? But there's definitely, this is a good example of, yes, they all will work, but one is way better than the other. It's like, one's like driving a Cadillac, the other one is like, I don't know, driving a bike without wheels. It would be much more challenging. So out of all of these choices, hopefully this guy right here, this y value, is going to be calling your name. Why? Because if I want to get that by itself, it's going to be pretty easy just to move the 5x and then get rid of the negative. Anything else over here, I'm going to have to divide through by the 7, and I can see right away that that's going to give me some fractions, or divide by the 4 if I get rid of that one. That's going to give me some anything else is going to give you some kind of messy work. It would still work, but it would be harder. So I am definitely going to go for this one right here. That means I'm going to move the 5x out of the way over to the right side. Make sure you do the opposite sign. And that leaves us with negative y. And then the negative 5x and the 2 over here. And then I don't want that negative. I want this fully simplified. Don't forget to, first of all, don't forget it, because it is still there. And second of all, take care of it, right? And we've been doing this for a little bit now here. You can either divide everything by a negative 1 or multiply by a negative 1. Either one of those actions will essentially switch all your signs. If you multiply through by a negative 1 or divide, it's going to rewrite this, and everything is going to be the opposite sign. But now we'll have what we need, which is a variable that is isolated and that I can use to substitute. So now that I know y is equal to 5x minus 2, I'm going to go a little bit faster here, then I can take that 5x minus 2 and I can insert it into the other equation where the y was. Since that is equal to y, I can plug it in for y. So let's do that. I'm going to rewrite that top one now, 7x minus the 4 times, but instead of saying times y, I'm going to write that 5x minus 2 right in there. And then I'll still have the 8. Everything else has got to stay exactly the same. okay? But now that I've done that, I can solve here. I can distribute the negative 4. So that's going to give me a negative 20x, and a positive 8 is equal to 8. I've got a couple of like terms here we can combine. That's negative 13x. And once we do that, we can start to solve. I'll get rid of the 8, which actually, by getting it rid of here, it does so over there as well. So that leaves me with 0. That is okay. And then I divide. And then 0 divided by anything is just going to be 0. So this is just x equals 0. That is the first part of our ordered pair. So I'll write that over here. And then to find the other value, I can go ahead and come in here, either of the originals or even this one that I reorganized, which is the one that I'm going to favor. Since that y is already isolated, I'm going to go y equals 5 times 0 minus 2 and solve this for y. Well, 5 times 0 is 0, and 0 minus 2 is just negative 2. So this was our solution in ordered pair right here. So if you don't have a variable isolated, you'll have to reorganize, pick one of them and reorganize it so you have a variable by itself. It doesn't have to be y, it could be x, it could be, and I could have picked any of these, but this was definitely the easiest. Okay, so now that we know substitution and we have our second method, let's talk about what that might look like in those special cases that we had discussed before. There are sometimes situations where our lines don't intersect at all, or they intersect everywhere because they're the same line. So it was pretty, I think, visually helpful to see that with graphing, but how would that kind of exhibit itself if we were doing it with this method? So let's try that. If we're doing substitution, I might, we probably don't realize it at the beginning, so we go on about our business to start this process. I check to see, I see y is by itself, so I'm like, all right, great. I'm going to take this, I'm going to insert it right in there so I can get started with this method. So I'm going to rewrite x minus that 1/4, and instead of writing a y right there, I'm going to plug in that 4x minus 2 into the place of the y. I'm going to leave everything else exactly the way it looks right now. Okay, and then, great. I don't have any y's, it's all x's, I'm ready to solve, so let's simplify and solve here. We'll distribute that negative 1/4, so x stays put, and negative times a positive here stays negative. 1/4 times 4 happens to just be 1. So this is a 1x or just x. So we're doing x minus 1x or x. And then also here, negative times negative is a positive, and 1/4 times 2 is 1/2. You can check all that in your calculator if you like, but it's true. All right, and then we go to combine like terms, and then hopefully some of y'all might already be, maybe your wheels are already turning like, wait a minute. Okay, when I go to combine like terms, I have a couple of x terms here, but x minus x is just 0, right? This goes away. If I have an x and I take it away, I have no more x's. So these guys, they cancel each other out, okay? And that's when we know it's one of those special cases. It's a lot like those special cases that we were doing when we were solving equations. That's what you were really doing. So this part, believe you didn't realize, but it's review. So if your x's disappear, what's of course really important to note is what's left behind. In this case, I have 1/2 equals 1/2, which I think we could all agree is absolutely true. And therefore, this means that this has all, infinitely many solutions, right? Let's make sure we use the right vocabulary. So infinitely many solutions. Remember those? We did those already, but now we're doing it in terms of systems. And how do I know? Because that is equal to itself. It is a true statement. So, and our variables disappeared. So that's how we knew it was a special type of case. Okay. So that's what that might look like. Okay, let's try one more. And let's try number 8 here. We want to solve this. We're going to use substitution, so I've got to get one of these by itself. Right now, nothing is by itself. And I think this x, honestly, is a really good option, although I could do any of them. So I'm going to move the 3y over to this side on the right with the opposite side. So that reorganizes this top equation as x equals that 12 plus a 3y. And once it's organized like that, and I know that X is equal to this quantity, I can take that and substitute it. Okay, like that. And so let's do that here. Let's see. So I'm going to just copy this. It's going to be y minus 1 equals that 1/3 parentheses. And then instead of x right in there, we're going to drop in that 12 plus 3y. And then the plus 6 is still after that. And then close that. All right. And then let's just, you know, the rest is history. It's all review. So parentheses first. We'll clean up a little bit in there. So I've got that 3y, and then 12 and 6 is 18. And then we'll distribute, so we'll take 1/3 of that, or divide everything by 3, basically, and that'll leave us with 1/3 times 3 is just 1y, and 1/3 of 18 is just 6. Okay. And now that both sides are simplified, we will isolate our variable. We'll pick one of these to get to cancel. But, oh, look at that, right? They were identical. After simplifying, we had exactly the same. And so in our effort to get rid of one, we get rid of both, and they disappear. Again, that's when you know. When they're both identical and they they disappear, they cancel each other out, you know you have a special case. In this case, though, we end up with a -1 on this side and a +6 on the other side of the equal sign. And we know that -1 is definitely not equal to 6. That is absolutely not, that's nonsense. So this is a no solution. Okay. All right, y'all, we're going to finish out with a word problem. And that'll be it. So let's do number 10 here very quickly. It says a video rental company offers a Super Saver plan that includes monthly membership fee of $10. And they charge $2 for every DVD borrowed. Okay. Then there's also the Movie Lovers plan, which is $15 a month and only $1 for every DVD rented. So let's come up first with an equation to represent the Super Saver plan. So the Super Saver plan has a monthly fee of $10 and then $2 for every DVD borrowed. So X is the number of DVDs, Y is going to be the cost, so that would be Y is equals to, we have that $10 starting fee and then $2 for every DVD. Or if we want to write that in slope intercept, just because we like the way that looks better, that's fine too. We're paying $2 per DVD plus that $10 membership fee. Okay, yeah, I think I like that better. And then write an equation that represents the Movie Lovers. Well, the Movie Lover plan says you pay a $15 fee and then $1 for every DVD rented. So there it would just be $1 per DVD. So you could just do 1X or just X, but there is that $15 monthly fee. Okay, so you can have the one there or not, whatever is easier for you. Then they want to know, well, how many DVDs do you need to rent each month so that these guys are equal to each other, right? So it's basically solving the system. When is this plan the same as this plan, right? We're just solving the system. And in this case, we're going to use substitution for good practice. Now, I have 2 isolated variables, so it doesn't really matter which one you pick. If I have this y by itself, then I can take this expression and drop it in there. Or if this y is by itself, I can drop it in there. It's up to you. Basically, we're going to set them equal to each other is really what's going to happen here. So if y is equal to 2x plus 10, then I can put that right over there and essentially set them equal. So instead of y equals, I'm going to write 2x plus 10 equals 1x plus 15, which kind of makes sense because we want to know when are they the same. So when are they equal to each other, these 2 plans? And that's really that's what we do when we do substitution. They're both simplified, so I just have to move my x's to one side. They're not identical, so this is not a special case. I'm going to be able to actually get rid of them on the right and just have 1x left over here. So it's going to look like that, and then we solve for x by subtracting the 10. So x is equal to 5. So basically, it's going to cost the same when we rent 5 DVDs. You can see that this is an older problem because nobody uses DVDs anymore. So there it is. So you would need 5 DVDs exactly so that both plans are costing the exact same quantity. And I might just do a follow-up and say, well, what is that quantity? What would be the price, right? And that's when we can plug them back in. Either one, it should work. So if I do 5 DVDs here for $1, that's $5, plus the 15, that's $20. And if I do 5 here, 5 times 2 is 10, plus the other 10 is $20. So they would both cost, $20. So, and graphically speaking, that would have been the ordered pair, right? At 5 DVDs, they both cost $20. That would be like the point or the ordered pair. That's substitution.